Okay, so as always, please, if you have a moment, just type your name into the chat so that I can get a record for your attendance and to make sure that you get your data on time for next week. Okay, so this is going to be a kind of probably not the worst thing to have for if the attendance is a little less today than usual, because I want to go and spend the whole day discussing circles, which was one of the three topics that people wanted to do a mini workshop on when we took a vote early on in the semester. So we basically finished up our logic workshop yesterday. There were a couple of exercises I sent. If you'd like to attempt them and send them to me, I will gladly comment on your work. I'm thankful to James for submitting it, and then Miata, who will submit it later. But I don't want to spend time today going over those exercises because with the limited time that we have, I'd like to spend it all on circles and circle theorems because I think this will be a pretty fast mini workshop. And then the third topic, which was differentiation and integration, we'll go spend a little bit more time on. Hopefully, we'll start that next week. Okay. So I just want to recall, what do we mean by these circle theorems? Well, generally refers to a collection of results governing governing the relationship between areas, angles, lengths, and arc lengths that arise from circles and lines drawn inside them. It's a very general definition. And if you look where they show up in the curriculum, they're referred to in three different parts of the curriculum. So a little bit in mensuration. This is the more basic results on circle theorems. Much more so in the unit on plane geometry and then a little bit also referred to in vectors and trigonometry. But somehow most of the meat of the curriculum for circles is in this plane geometry unit, and that's where we're going to mostly focus. Okay. And now, if you do look at the curriculum, it doesn't say very much. It really just says circle theorems, and it doesn't say anything beyond that. So, part of designing a workshop on circle theorems is to try to decide which theorems you're going to do, which are the most important theorems to focus on. And really, today's class is the only full day we'll spend on circle theorems. We may spend a little bit of time next week on it, but it's not going to be the main focus of the day. Okay, so we'll have to choose somewhat carefully what to cover. We're not going to be able to spend lots of time on every single circle theorem that there is. So we have to spend a little time thinking of, what we really want to do. Okay. So this is a slide that I gave last time. So how do we want to divide circle theorems? Well, I would think of it as basically you have your basic theorems and you have your advanced theorems. And so basic theorems, I mean just the very standard formulas for circles, so formulas for area and circumference. And then maybe the next most basic would be formulas for the measures of central and inscribed angles. Okay, these would all be under kind of, mensuration. Okay. And then there are various more advanced formulas for circles. I'm not claiming that this list is exhaustive, but one of the things would be formulas for angles involving tangent lines and crossing chords, formulas about ratios of line segments inside circles. This is something called the power of a point theorem, which is kind of an amazing theorem, but it's actually very easy to prove. And then maybe some other theorems about inscribed triangles and quadrilaterals. And if you want a reference for basically everything that we're going to do, it's covered here in chapters 9 and 10 of the book that I sent over the chat a while ago. So, this Art of Problem Solving, Volume 1. So, chapters 9 and 10 cover these circle theorems, and they also cover a little bit more. So, the chapter 10, I'll say, also covers, where's the, yeah, also covers theorems about angles and parallel lines. Okay, we won't really discuss that today, but it also does cover theorems like this. Okay, so if you need a reference for what we're doing, there are many, many references. You may have access to a textbook that talks about this, but one place that you can read about it is chapters 9 and 10 of this Art of Problem Solving book that I sent out to everybody. And if you need another copy, I can always send it out again, the PDF. I've probably sent it out on the list about 5 or 6 times at this point, but it is no problem to send it again. Okay. So I asked whether people wanted to focus more on the basic or more on the advanced theorems, and I didn't get a lot of answers, but I did get one answer saying that they wanted to start with the basic theorems. So when one person votes, that person wins the vote. So I will spend a little bit of time on the basics before going to the advanced theorems. But given that, the theme of this week's workshop is kind of making you actively think about how to design the workshop, what's the important material. Um, I want to, before we actually start on the content, I want to just spend a moment discussing what is it that we want to know about circle theorems, or in particular, what should a teacher know about the circle theorems? Well, certainly, a teacher should know the main results about circles as mentioned on the previous page. A teacher should, of course, be able to calculate the area and circumference of a circle and know how to measure an inscribed angle or a central angle. These basic things are things that a teacher should know. Ideally, the teacher should also know something about why these results are true. I'm not saying that every teacher should have a perfect proof immediately memorized and ready to go, but there should be some intuition at the very least about why these results are true. Okay, so not necessarily a full proof, but it also shouldn't be complete magic. It's better if you have some clue about, what makes these results true. And when there are problems based on these results that involve some algebra, a teacher should be able to solve these types of problems. Okay, this is maybe reminiscent of what we talked about in the fall. Okay, so should be able to solve these problems. And so for each of the results that we covered today, in addition to giving the results, and occasionally we'll do an exercise, I'm also going to mention how much justification I think a teacher ought to be able to give for the given results. So again, this is not, the word of God. This is my subjective opinion. Okay, so you may disagree with me, and I may my expectations may be unrealistic, or maybe they're too low. Who knows? But this is for each of these circle things. This is what I think that if you're going to teach it, if you're going to teach it, you know, and you want to really know what's going on, I think this will if you have this level of knowledge, you will be well prepared to answer questions from the students that you get. Yes, and so Enoch, I saw, yeah, you came in a little late, but before that we discussed, it just says circle theorems, but it doesn't tell us what they are. So part of today is, we're trying to understand what are these circle theorems and what are the most important ones. Okay, so we're going to try to get through a lot today. We'll try to do the basics and the more advanced stuff. Okay, so let's start with the most basic theorems. So we're going to start with some notation over here. These are things we've done in the past, right? So if we have a circle, we're going to call R the radius, D the diameter, C the circumference, and A is going to be the area. And so we have these two basic results that, of course, everybody should know about circles, math teachers and anybody else in the world, right? So the circumference of a circle satisfies that C is pi times the diameter, or 2 times pi times the radius, same thing. And the area of a circle satisfies area equals pi r squared. Okay? So these are basic formulas. And I think it's somewhat important to know that somehow the second formula is much more difficult than the first formula. They're not just twin formulas where this one has a squared and this one has a 2. Because what is the justification? Well, the circumference formula is the definition of pi, right? What happens if you rearrange this? This gives you that pi equals c over d, or in other words, c over 2r, right? Because the diameter is twice the radius. So there's no proof of the first result because the first result is a definition. What is pi? Pi is If I draw a circle, pi is the ratio of the circumference to its diameter. That's what it is. And this ratio is constant because the circumference and the diameter are one-dimensional quantities. If you remember a little bit about what we did in the mensuration unit in the fall, we showed that if you multiply, since they're both one-dimensional quantities, if you multiply the diameter by some, like if you double it, for instance, you're also going to double the radius, I should say, the radius and the circumference. Right? So if you double the diameter, you double the radius and you double the circumference. If you triple the diameter, you triple the circumference. If you divide the diameter by 10, you divide the circumference by 10. But the point is that the ratio always stays the same. If I take circumference over diameter, whatever I multiply the diameter by, the circumference is multiplied by the same amount, which means that that ratio is always going to be the same. Okay? So, and that ratio is just some number, and so we give it a name. And the name that we decide to call that number is pi. And it's about the password for this Zoom room, right? Now, the area formula is more difficult. So the area formula, if formally, the way you have to justify it is to use calculus. Okay? So the area formula is justified and proven using calculus. And I think we mentioned this last time how to do this, but I'm not going to go back and do the calculus proof today, but I do want to say a little bit, and I don't think it's necessary that every single high school math teacher knows a calculus derivation of the area formula of a circle. It's nice to know, but I think it's not realistic that everybody will be able to do it. But what I think you should know is some sort of basic idea for why pi r squared makes any sense for the area of a circle, right? I mean, you don't want it to just be, it's not complete magic. There is a way that you can see it. And one way that I think can help is there's a video here. The video is 1 minute long. So I think maybe we'll watch it. Um, I'm going to go share my screen for a second. So I'm going to go get the video up here. V equals LZA 312 PEC TW. Okay, so I'm going to pause this video and I'm going to share my screen to show it to you.
Hi, this is Presh Holliker.
Sorry.
Let's derive.
Okay. Let me share my screen here.
Yeah, that good
Yep.
afternoon.
Yes.
Yeah, is there also possible that the video that you coming to play share with us in the chat room as well?
Sorry, in the chat room? Yes. I mean, it's here, but yeah, if you want to actually, if anybody wants to just copy down the address, you can just paste it to the chat room. This is the address, so it's in the notes if you want to find it. But
Okay.
I'll play it in the chat
Okay.
room at some point. But let me try this. Okay, and let me first. I need to admit people to the waiting room. Okay, so let's try this. The video may be a little fast. It's because it's only 1 minute long, but we will.
Hi, this is Presh Holliker. Let's derive the area of a circle intuitively. We'll start out by drawing a circle, which we'll subdivide with 16 wedges. We'll rearrange the wedges into a shape that's more familiar to us. Specifically, we'll rearrange them into a rectangular shape. The base of this rectangle is the radius of the circle, and the height is half of the circumference because both sides together make up the circle. Since the circumference is 2 pi r, half of it is pi r. The area of a rectangle is its base times its height. We substitute in the values, and then we multiply to get the area of a circle as pi r squared. This formula becomes exact when we make the slices infinitely small. Please subscribe to my channel. You can support me on Patreon.
Okay. So that's a very, very quick 45-second introduction to what's going on. So let me try to go through this slightly more slowly because I think that's a little fast for people. Let me just share my screen again. Okay, share. Why can I not share? Sorry. Oh, sure. Here we are. Screen. Hold on. Let me put this on. Okay. Okay. Um, okay, so let me go through a little bit more slowly what's actually going on in this video. And if you want, you can watch the video over and over again until you get it. But basically, the idea is if I draw my circle here, and I have a circle, and the radius here is r, that's the radius, and we already know that the circumference is equal to 2 pi r. Okay? And so what happens now is if I divide the circle into a bunch of little wedges, they used 16 in the video, but there's not really anything super important about 16. Just divide it into as many as you want. And then if you rearrange the wedges of the circle, you can rearrange them so that they kind of look like this. You kind of put them in alternating directions. Right, and so on. And in the end, you have some final wedge down here. Okay, so you're rearranging the wedges. Right? And then what you have here is this looks pretty close to a rectangle. Of course, it's not exactly a rectangle because these wedges are curved. So everything is curved a little bit here. And this is diagonal, so it's not exactly a rectangle, but it's pretty close. And the more wedges you divide it into, this gets closer and closer to being a rectangle. Okay, I mean, it's effectively this proof is calculus, but it's calculus without the symbols and without the algebra. You're still doing the idea of taking a limit. But if you don't like calculus, then you can just imagine, well, if I make the wedges really small, this thing gets pretty close to a rectangle. And what are the dimensions of this rectangle? Well, on one side, this is just the radius, r, right? Because we're taking a wedge, and this is a radius of the circle. And then what about the outside? Well, these wedges are arranged so that half of the wedges give you this side when they're all put together, and half of the wedges give you this side when they're all put together. So, Saley, I'll give you, I'll answer your question in a second. So, this over here is going to be 1/2 of the circumference. Or in other words, pi r. And on the other side, you also get 1/2 of the circumference. Okay. And so the area of the circle is equal to the area of the rectangle, right? Because all we did was slice it up and rearrange it. That's not going to change the area. And the area of a rectangle is going to be, well, we have r is one side times, well, 1/2 of the circumference, which we saw was pi r. And this gives us pi r squared. So to answer Saley's question, you can't say that a equals pi d because r squared is not d, right? 2r is d. R squared is just the square of the radius. It is what it is, right? So I think this kind of justification it's pretty easy to remember, and it's a good thing to keep in mind. If you don't want to do an actual calculus derivation of the area of a circle, then this is a pretty convincing, I think, geometric justification for why it should be pi r squared. Because basically, if you chop up the circle into little wedges, you can arrange them to make a rectangle that is r on one side and pi r on the other side. And that's going to give you the area of the circle. Okay, so the area of the circle here is equal to the area of a rectangle. And I find this picture pretty, dramatic. Like it's a picture that I remember very well. And if you want, you can rewatch the video a few times to get it cemented. But I think this is a good justification for why you get pi r squared. Okay, any questions? Okay, if no questions, good. Okay, so we can do an exercise, just a basic exercise for practicing with the basic formulas. So suppose we're given a circle with circumference C and area A. And if a new circle has area 3A, then what is its circumference in terms of C? Okay, right. So, I mean, the way you can do this kind of organically, but probably the most straightforward way to do this is to solve for the radius of the old circle and the new circle. Okay, so this would be one way to do this. So the old circle, right? So the radius is going to be equal to, well, you have arrow, maybe I'll write it like this. We have that A is equal to pi times the old radius, which I'll call r sub old squared. Or another way of saying that is that A over pi equals r sub old squared, or square root of A over pi equals r sub old. Okay, so this would be one way of solving this. Old circle square root of A over pi equals r sub old. New circle, well, now this one has area 3A, so this is equal to pi r sub old, sorry, r sub new squared, uh, which gives us that 3A over pi equals r sub new squared. And that gives us that 3A, square root of 3A over pi is equal to r sub new. Okay? So what do we have? We have that r sub new, and another way of doing this, right, is we can write this as square root of 3 times square root of A over pi. Now, the square root of A over pi here is r sub old, right? This is the old radius. And so the upshot of this is that r sub new is equal to square root of 3 times r sub old. Okay, so by comparing the area of the old circle and the area of the new circle, we see that the radius of the new circle is square root of 3 times the radius of the old circle. So now, what do we know? The question doesn't ask us about the radius, right? The question asks us about the circumference. Okay? Question asks us about the circumference. Okay, so we know that the radius of the new one is square root of 3 times the radius of the old one. So let's now do circumference. Well, what is the new circumference? I'll call it C sub new. Well, by the circumference formula, this is equal to 2 pi times the new radius. But we know that the new radius is equal to square root of 3 times the old radius. So that's 2 times pi times square root of 3 times the old radius. And well, C is the old circumference. C is equal to 2 pi times the old radius. This is C, right? That's the old circumference. So this is going to give us square root of 3 times the old circumference. And so this is what the question is actually asking us for, right? A new circle has area 3A. What is its circumference in terms of C? Well, the new circumference is equal to square root of 3 times C. So this is the relationship that we want. Okay, so the new circumference is square root of 3 times the old circumference. If you remember back to October when we were doing these mensuration theorems and talking about dimensional analysis and one-dimensional quantities versus two-dimensional quantities, this may be fairly familiar. So if you go back and look at your notes on that, you'll see that we did a problem very similar to this. Okay, but the point is, you're given stuff about circumferences and areas, but our formulas give both of those in terms of the radius. So if you want to go from circumference to area, usually you need to go through radius, right? So you're told something about area, you want to get something about circumference. First, you have to say something about radius. That's this part over here. You're getting formulas for the radius in terms of the areas. So the old radius is square root of a over pi, and the new radius is square root of 3a over pi. And then once you can say something about how the radii relate to each other, you can then say something about how the circumferences relate to each other. Okay, so any questions about this problem? Okay, great. Okay, so let's move on. Okay, so what's the other basic mensuration theorem is angles. Okay, so suppose we're given a circle with center O and an arc AB. So I'm going to draw this picture. So we have a circle over here, and the center of my circle is O. And then I'm going to take 2 points on the arc. I'll take 2 points on the circumference of the circle. Let me actually try to do these better. So this point is going to be A, and this point is going to be B. So what is the measure of the arc AB? So the measure of the arc AB is defined to be the measure of this central angle, which we call AOB, right? Sorry, go over the previous problem for clarity.
Yes.
Yes. Okay. Sure. Okay. So we have our old circle has circumference C and area A. Our new circle has area 3A, but I don't tell you what the circumference is. So the question is, what is the circumference of the new circle? Okay, and I mean, you're not going to be able to give me a number because I haven't given you any numbers. So the best that you're going to be able to do is tell me what this circumference is in terms of C. Okay, and so what I'm saying is that the most straightforward way to do this is to solve for the radius of the old circle and the radius of the new circle. And the way we do this is that we have a formula relating the area to the radius. So A is the area of the old circle. And we know, so R sub old, really, I should maybe say, let R sub old equal radius of the old circle. And I won't write it down, but of course, R sub new means the radius of the new circle. Okay? So for the old circle, we have A is pi times R sub old squared, right? Pi R squared. That's our formula for the radius of a circle. And now we can just solve for R old, right? We divide both sides by pi, and then we take the square root of both sides. We get that the old radius is square root of A over pi. Similarly, we work for the new circle. The new circle has area 3A. That's given. So that's going to be pi times the new radius squared. Again, we divide both sides by pi and take the square root of both sides. So we have that square root of 3a over pi is the new radius, and we can always factor out a square root of 3. So that's going to be the same thing as square root of 3 times square root of a over pi, right? So the old radius is square root of a over pi. The new radius is square root of 3 times square root of a over pi. So the new radius is square root of 3 times the old radius. So that's the first step. There's two steps. So in the first step, we derive that the new radius is square root of 3 times the old radius. Okay, that's what we have here. This is step 1. Now for step 2, we're trying to actually solve the problem. We want to know what is the circumference of the new circle in terms of the circumference of the old circle. The circumference of the old circle is c. Well, what do we know about the circumference of the new circle? Well, we need to use the formula, right? The circumference of the new circle is 2 pi times the radius of the new circle. We want to get this in terms of the old circle. Well, 2 pi times the radius of the new circle, well, the radius of the new circle we've already seen is square root of 3 times the radius of the old circle. So we get 2 pi times square root of 3 times the radius of the old circle. But now we realize that 2 pi times the radius of the old circle equals the circumference of the old circle, which is c. So this expression here, remember the question said we want it in terms of c. So this expression here simplifies to just square root of 3 times c, times the circumference of the old circle. So this gives us the answer. We're saying that the new circumference is equal to square root of 3 times the old circumference. That's the answer that we're looking for. Okay? Is that okay? Okay, great. Okay, let's move on. Okay, so back to this. So we're talking about angles. So the measure of the arc AB is defined to be the measure of the angle. So if this angle is 70 degrees, then the arc is also 70 degrees. Okay, we measure these arcs by degrees. So the measure of the entire circle would be 360 degrees. And then whatever angle you have in here, the measure of the arc is the same thing. Again, this is just a definition. Okay, it's not a theorem to say that a central angle of a circle equals the measure of the arc that it cuts off. There's no content there. That's just the definition of what a measure of an arc means, right? So this does not require any justification. But now, if I draw a similar, oh wait, let me do this in blue. If I draw another circle, and I have A and B, and now if I take C, let's say I have 3 points, and now let me look at the measure of angle ABC. So it turns out that the measure of the angle here is half the measure of the arc. So this is called an inscribed angle. And what this says is that the measure of an inscribed angle is 1/2 the measure of the arc that it subtends. And what do I want to say? Yeah, and so this, so I'm going to say here, this does not require justification. Because it's just a definition. But this does require justification. Right? This is not obvious that this is true, that if this arc measures 60 degrees, then the angle is 30 degrees. Right? This is not at all obvious. Whereas this, I don't want to say it's obvious, but it's free of content. This is literally just the definition of what arc measure means. It's the same as the angle. So it's fine to not have a proof for this. No proof can exist because this isn't really a theorem. It's just a definition. But this is a theorem. This is saying something about how this arc measure relates to this angle.
Yeah.
Those are two different things. Yes.
Hello,
Enoch.
there.
Yep.
Hello.
Yep. Mm-hmm. Enoch. Yep.
Hello.
Hello. Yes. Yes. I hear you.
Yeah. Yeah. In the first diagram, I really want to ask a question because like certain thing I always been thinking based on certain contradiction. I want to inquire something.
Mm-hmm.
You hearing me? Yeah. Okay. So yeah, I want to know if does the measure of angle AOB equal the measure of the arc length AB?
Well, it's not the arc length. And the arc length, that depends on the radius of the circle, right? But what we say the when we say the measure of an arc, we don't actually mean the arc length. We mean the measure of the arc in degrees, right? And when we talk about the measure of an arc, we're talking about degrees or radians. So in that case, they are equal, right? If the angle is 50 degrees, then the arc is 50 degrees. Now, the actual arc length might depend on the radius. You know, if the circle has radius 1 or radius 2, then the actual arc length in terms of calculus will be different. But as far as what we say, when we say the measure of the arc, we don't mean the length, we mean the angle measure. And in this case, that's the same as the central angle. So if the central angle is 50 degrees, we say the arc is 50 degrees. So, does that answer the question? But of course, if you have a 90-degree angle and you have a circle of radius 1, then the arc length will end up being pi over 4. Whereas if you have a circle of radius 2, the arc length is going to be pi over 2. So there you get different arc lengths depending on how big your circle is, but the angle is always the same, and the arc measure is always the same. Other questions?
Hello, sir.
Hello, yes, Rush.
We are at the theory God. For me, I just come in got a network breaking first.
Okay.
This is theory we own, right?
Mm-hmm.
With the circle, right?
Yeah, is what correct? Sorry.
Okay, no problem.
Okay. Yeah. Okay. All right, so this requires justification. Okay, and it's good to have some sense of why, again, why this might be true. So, what is the justification? Well, that a central angle has measure equal to its subtended arc is a definition, so it does not require justification. But the results about inscribed angles does require justification. Okay, and it's worth it to give what I'd say is a partial proof to get this to work. So let's look at what I'm going to do is I'm going to break this into two cases. We're going to do kind of a proof by picture. So first case, so let's say that I have my circle here. I might need to use more of the page for this. So let's say I have my circle here, O, and now let's say that my angle involves a radius. So let's say that I have A, and this is C, and this is B. And let's imagine that the center actually lies along one of the angle sides. So the first case would be center lies on one side. Okay. And this is some angle. I'm going to call it theta. We want to figure out this angle theta. Okay, well, one of the things that you do to do proofs in geometry is often it helps to draw a line that's going to elucidate what's going on in the situation. And what I can do here is I can draw this line over here connecting O and C. Is I'm going to draw the line OC. And then one thing that we should observe, so I'll write this over here. Let's observe that the triangle BOC, well, what do we know about this triangle? Well, this side is a radius, and this side is a radius, right? And that means they've got the same length, right? The lengths of these sides are both R. Whatever the radius of the circle is, they both have the same length, right? Or in other words, a triangle BOC is isosceles. Right? Because I drew this triangle where two of the sides are both radii, so they've got the same length. It's an isosceles triangle. And one thing we know about isosceles triangles is that the angles opposite the equal size, right, are also equal angles. Right? So what that means is that angle, I guess we'll call it OCB, equals angle OBC, which is equal to angle ABC, which is equal to theta. Right? Because this angle over here is the same as this angle, right? Because they're the corresponding angles of an isosceles triangle. And the big angle is the same as the little angle because it's just the same line, just extended. It doesn't affect the angle. So we know that this angle here is theta. Okay? So what do we know? So I'm going to give this angle here a name. I'm going to call it alpha. Let me call this angle alpha. Right? And so what do we get? Well, these three angles have to add up to 180 degrees. So alpha plus 2 theta is equal to 180 degrees. Or 2 theta is equal to 180 degrees minus alpha. Right? If I add all of this up, I get 180 degrees because it's a triangle. So now lastly, let me look at this angle over here. Maybe I'll call this angle here beta. Well, what do we know about alpha plus beta? They make a straight line, right? Alpha and beta make a straight line. Beta is what's called an exterior angle of the triangle. But because they make a straight line, they have to add up also to 180 degrees. So I'll say also alpha plus beta equals 180 degrees, or beta equals 180 degrees minus alpha. Right? Because you add these two things up on a straight line, they've got to be 180 degrees, right? So here you've got a triangle is 180, and here you've got that a straight line is 180. Okay? Well, okay. 2 theta is equal to 180 minus alpha, and beta is equal to 180 minus alpha. So if we set equals to equals, we get that beta equals 2 theta. So equating, we obtain that beta is equal to 2 theta. But what's beta here? Beta here is the central angle, and theta is the inscribed angle. So what this tells us is that if beta is the central angle, that means that the measure of arc AC is also beta, right? Because beta is a central angle. So since beta is a central angle, we have that arc AC has measure 2 theta. And well, this proves the theorem. Right? Because we're trying to prove that the arc measure is double the angle measure. Or in other words, the angle measure is 1/2 the arc measure. But we just showed it, right? We showed that if the angle is theta, then the arc is 2 theta. That's telling us exactly that the arc is 1/2 the measure of, that the angle is 1/2 the measure of the arc. Okay, so this is a little bit of a tricky proof, right? You've got to draw it this way, you've got to draw this extra line, and then you have to use these two ways of making 180 degrees, right? One way is coming from adding up all the angles in a triangle, and one way is coming from adding up the two angles that make a straight line. But when you have this, what you end up being able to do is setting beta equal to 2 theta. And that's exactly what you want. Setting beta equals to 2 theta is exactly how you get that this arc measure is twice the measure of the angle. Okay, so this tells us, or the way James phrased it, which is another valid way of thinking about it, this tells you that the central angle is double the inscribed angle that intercepts the same arc. Okay. Now we haven't proven the whole theorem, right? Because I made an assumption. My assumption here was that the center lies on one of the lines. So I'm going to need a second page of this proof that's actually going to prove things in general. But before I do that, are there any questions about this case here?
Dr. Obus?
Yes, Jasper.
Yeah, so I have a concern where you have also alpha plus beta is equal to 180 degree or beta is equal to 180 degree minus alpha equating. So what exactly were you equating to obtain beta equals 2 theta?
Well, we have these two equations, right? We have 2 theta equals 180 minus alpha, and we also have beta equals 180 minus alpha. So since they're both equal to the same thing, they have to be equal to each other.
Oh, okay, all right, okay.
Right, since they're both equal to 180 minus alpha. Yeah. Okay, other questions? Yeah, so we see that the central angle has measure twice the inscribed angle. Okay, so what do we do in general? So if we accept this, so in general, what do I do? I'm going to draw a circle. My circles aren't so good, but that's fine. So here's the center, and now let's just say we have an angle like this, A, B, C, where now we don't have that either line passes through the center. Well, what I can do now is just draw the line through the center. Okay? And maybe I'll call this point D. So maybe I'll put it as a solid line. I'm going to draw this line through the center, and I'm going to call this line D. And let me write two angles here. Maybe I'll call this alpha, and I'll call this angle beta. And well, what we know is from case 1, we know that... Yes, question?
Yeah, it's Enoch.
Yes, Enoch. Yeah.
Yeah, just one again. Because this diagram is not really drawn to scale. So I want to know if the measure of ABD equal to the measure of DBC, which is if angle alpha is equal to
not
the measure of
necessarily.
angle beta.
I'm not claiming that. I don't want to give that impression. They're not. There's no reason for them to be equal.
Okay.
Yeah. No.
Okay then.
But what I am claiming is that the measure of angle alpha is equal to the measure of arc AD, or is equal to, I'll say 1/2 times the measure of arc AD. It's equal to 1/2 times measure of arc AD. Right? Because this is the theorem that we had, right? This angle does go through the center, so the angle alpha has to be 1/2 measure of arc AD. And likewise, beta is equal to 1/2 times the measure of arc DC. Right? Because again, we have one of the lines is going through the center. So what do we get? We get that alpha plus beta is equal to 1/2 measure of arc AD plus arc DC, right? We just add these equations to each other, right? So measure of arc AD plus arc DC, but what is arc AD and arc DC? When you add them together, that's just arc AC, right? So this is equal to 1/2 measure of arc AC, right? And this is exactly what we want. We've showed that alpha plus beta this is angle ABC, is alpha plus beta, and we've shown that it's equal to the measure of arc AC. So all that we have to do is we proved it only when one of the angles goes through the origin, but if neither side of the angle goes through the origin, you just draw a line that does go through the origin, and that splits the angle up into two pieces. and then you're fine. Once you've done that, then you just apply the theorem to both pieces and add them up, right? So on the first side, you get that this arc length is twice this angle length. This arc measure is twice this angle measure. And on the second side, this arc measure is twice this angle measure. So when you add it all up, the total arc measure is twice the total angle measure. Okay, so this gives the proof. Okay. Okay, so this gives the proof. Okay, so the real work is in the first case where one of the sides goes through the origin, and then now for this second proof, you need to draw a line through the origin to make it work. So if you're teaching central angle theorem, I'm not saying you need to walk around in your daily life having this completely memorized, but even if in your class time you may not have time to go through the proof, depends on how much time you have, what's going on in class, how far you're ahead or behind in the curriculum. It's a good idea, at least before you teach this, to remember this story, to study this story and remember it. Because you may get a question. A student may ask, okay, why does this work? And I think this is the simplest proof. There are other proofs. In fact, the book that I sent gives a different proof. But I think this is basically the simplest proof. And I think it's worth trying to, when you teach it, remember this story. It's not too much. So remember this story of the first proof when you have that a line goes through the center, and then the second proof, which is just split the angle up into two parts where the splitting goes through the center. Okay, so this is our justification that an inscribed angle is 1/2 the measure of the corresponding central angle, or what's the same thing, 1/2 the measure of the arc that it intercepts. Okay, any questions here?
So that was it.
Yes, Rash.
All right. Not question for this, man. I just want to know because the last time I heard you talking about age problem, right?
Mm-hmm. Oh, no, we're not talking about, no, age problems. No, I think somebody suggested it as a logic problem type of thing, and I said that it didn't really fit in the logic. It's not really
Okay.
part of the logic curriculum.
Okay.
Yeah.
So like, is a geometry one, right?
Yeah, so we're on not even geometry in general, but very specifically circle theorems. So the
Circle
three
theorem.
topics that people voted for at the beginning of the semester were logic, circle theorems, and differentiation and integration. So
All
those,
right.
those are the three topics we're going to do.
Okay.
Okay. All right. Other questions? Okay, so this is a good theorem, and I mean, of course, the result you should know always, but I would review this proof before teaching it because I think it's a pretty nice proof, and it shows how drawing a line can help you in a geometric diagram, and it shows how doing a special case can then generalize here to a general case. Okay, so that's the inscribed angle theorem. So what's a consequence? What happens when we have an angle inscribed in a semicircle? So I'm going to draw an angle here. I'm going to draw a semicircle here. And let's say I take an angle inscribed in a semicircle. Let me draw this. Let me draw that a little better. What do I want? No, sorry. Let me try that. Okay. No, you know what? I think this technology can do things better than this. Let me actually try to draw a real circle. Do this. Will it give me a circle? Yes. Okay, it gives me a real circle. Great. Okay, so now let's say I draw radius here. And now let's say I draw an angle inscribed in a semicircle. Okay. So the question is, what is the measure of this angle? Well, this is a semicircle, right? Yes, it's true even when the angle is split by the center of the circle, exactly. Well, we can use the inscribed angle theorem, right? If I call this A, B, and C, so this angle is inscribed in a semicircle, well, arc AC has measure how many degrees? So this is a semicircle, right? So this means this is a radius. So we've got half the circle. So how many degrees is this arc?
Can we say 180?
Exactly, yeah. So this has measure 180 degrees. So angle ABC, what's the measure of that angle? Well, this is an inscribed angle that cuts off an arc that has a measure of 180 degrees. So we use our formula, right? It's got to be 1/2 times 180 degrees, or in other words, 90 degrees. Right? This angle is 1/2 the arc. Well, that's 90 degrees. Well, that's pretty cool, right? That's a right angle. So our consequence here is that every angle inscribed in a semicircle is a right angle. Okay. So this is an immediate consequence of this inscribed angle theorem, is that every angle inscribed in a semicircle is going to be a right angle, because it always cuts off an arc of 180 degrees. It doesn't matter where point B is. You can move B, you can drag B along the semicircle. It doesn't matter what point you go. The arc is always going to be 180 degrees, and that means the angle will always be a right angle, right? If I want to draw some other angle inscribed in a semicircle like this, sorry, if I do this, and then I draw some other angle inscribed like this, right? This thing's also going to be a right angle. Right? Whatever my theta is here, it's going to be the same thing, because these two angles intercept the same arc. Both of them is arc AC, which means they've both got to be 90 degrees. And this is a general thing with circles. If you've got inscribed angles that intercept the same arc, then they've got to have the same angle measure, because they're both 1/2 the measure of the arc. Okay, so this tells us that any angle we have in the semicircle is going to be 90 degrees. So if the first one is 90 degrees, the second one is also going to be 90 degrees. Right? Okay, so all of these are right angles. Any questions? Saley? Sorry, I'm not getting you. It's not coming through. Sorry, no, I'm not getting you at all. Sorry. No, it's all static. Okay, sorry, Saley. If you want to type something, you can type it in the chat. I'm not getting you. Okay, so every angle inscribed in a semicircle is a right angle. Inscribed angle is half of its intercepted arc. Exactly. Right. That's what we proved that's what we proved over here. So the inscribed angle is half the measure of the intercepted arc. So we proved it, and now we applied it. Right. So a result, a proof, and an application. Right. It's kind of the classical way of doing things. So this tells us, and in the case of a semicircle, it's not just half, but you get this interesting result that it's always a right angle.
No, this is true. She's not lying, actually.
Okay. Okay, moving on. So advanced theorems. Okay, so here's another angle theorem. So I'm going to move on from inscribed angles. Okay, so here's an interesting theorem. An angle formed by two chords. Okay, so let's say I'm going to draw another picture. So another circle. Draw a pretty big circle. Great. So I'm going to draw my circle, and I'm going to draw two chords meeting, not necessarily through the center. So I have one chord of my circle here, and I have another chord of my circle here. And I'm going to call these A, B, and C, D. Okay, and let me mark this angle as theta. Okay? And my claim is that, so i.e., I claim that theta is equal to the average of the measures of the two arcs, the arc on one side of theta and the arc on the other side of theta. So it's going to be 1/2. I'll write this measure of arc AC, 1/2. M stands for measure, so measure of arc AC plus measure of arc BD. Okay, so I claim this is a so I claim that this is how you figure out the measure of an angle that's just formed by two chords. Okay. Okay, so it's you take the average of the angles on the average of the arc measures on the opposite sides. So again, this is definitely not obvious. And why is this true? Well, I'll tell you, I'll do it on the other page, but the idea is to draw line BC. So a lot of times you draw lines. So what I'm going to do is say, so the actual idea is to draw, no, what I want to say, to draw this line BC. Okay, is to draw this line BC. And I'll show you on the next page why this works, right? So as James writes, it's the average of the measures of arcs AC and BD. Okay, so why does this work? So the justification, I'm going to redraw the picture. So let me redraw the picture here. I'm going to redraw it a little smaller. Okay. So I've got, let me just try to draw it so they look kind of the same. Okay, so I've got AB. And I've got CD. And this is my angle theta. And so now I'm going to draw this line BC. Okay. Draw this line BC. So now let me draw two more angles. I'm going to call this angle alpha, and I'm going to call this angle beta here. So I've got alpha and beta. Right, I've got alpha and beta, and I've got theta. And then maybe I'll label this angle gamma. It's going to be gamma. Sorry, it's a little bit small. It's alpha, beta, and gamma, and theta. Okay, so similar to what we had before in the first proof. Well, again, we're going to use that. We have lots of ways of getting angles that add up to 180 degrees. So let me observe. Well, first we have that alpha plus beta plus gamma equals 180 degrees. Or in other words, I'll say that alpha plus beta equals 180 degrees minus gamma. And also, well, theta plus gamma equals 180 degrees, which tells us that theta is equal to 180 degrees minus gamma, right? This should remind everybody of this first proof over here, right? Here I had alpha plus 2 theta was 180, and alpha plus beta was also 180. So we're using the same equations here, right? So we're using the same equations. Here we have alpha plus beta plus gamma is 180 because it's a triangle, and also theta plus gamma is 180 because it's a line. So that means both of these things are equal to 180 degrees minus theta. So we do the same thing as before. Equating, we find that theta is equal to alpha plus beta. Okay, that's good. So now, well, what's the measure of angle alpha? Well, what kind of angle is alpha? It's an inscribed angle, right? It's an inscribed angle with arc AC. So that means the measure of alpha is 1/2 the measure of arc AC. So I can say by the inscribed angle theorem, we get that alpha is equal to 1/2 times the measure of arc AC. And similarly, what's beta? Well, beta is an inscribed angle, and it cuts off the arc BD. So, and beta is equal to 1/2 times the measure of the arc AC. Sorry, not AC, BD. Okay, because these are both inscribed angles, and this is the one arc and this is the other arc. Well, remember, what's the theorem that we want? We want to figure out what theta is. Well, theta is alpha plus beta, and now we have that alpha is 1/2 arc AC and beta is 1/2 the measure of arc BD. So putting this all together, I can say since theta equals alpha plus beta, we conclude that theta equals 1/2 measure of arc AC plus 1/2 measure of arc BD. And when you factor it, that's the same thing as 1/2 measure of arc AC plus measure of arc BD. Right? And this is what we want. Okay, that's fine, Jasper. I'll let you back into the room if you leave and rejoin. So this is that. And this is exactly what we wanted to prove. Go back, we wanted to say that theta was 1/2 the measure of this arc plus the measure of this arc. And now when you draw this angle, that's exactly what you get. You get the theta, you first show that it's equal to alpha plus beta, and then you rewrite alpha and beta in terms of these arcs. So I'll just say we are done. Okay, so this is the entire proof. Okay.
Yeah, done.
Yeah.
How are you?
Yes. Hi, Emmanuel.
Okay. Yeah, okay. You were talking about theta is equal to alpha plus beta.
Right.
Is that what you said? I'm looking at how you said theta is equal to alpha plus beta.
Right.
But is that described or what you have there? But describe angle.
Right. So theta, that's the point, is that, sorry, theta is not an inscribed angle, right? Because theta is formed from two chords. It's not an inscribed angle. But alpha and beta are inscribed angles, right? Because beta is BCD and alpha is ABC, right? So these are inscribed angles. So the whole point of the proof is to take this thing here that's not an inscribed angle and write it as the sum of two angles that are inscribed angles. And once you can do that, then you can use the inscribed angle theorem, right? I can't use the inscribed angle theorem for theta because it's not an inscribed angle. But beta and alpha are. And so if we transform theta into alpha plus beta, then we can use the inscribed angle theorem to get this arc result for theta.
Okay, thank you.
You're welcome. Other questions?
So a follow-up question, Dan.
Yep.
Are you there?
Yeah, I'm here. I get you.
Okay, you said I'm looking at theta is in a circle. I'm also looking at alpha and beta. But you are saying that what qualifies the two of them to be an inscribed while theta is not?
Because for the angle, the vertex of the angle for beta is on the circle. And the vertex of the angle for alpha is on the circle. But for theta, the vertex is not on the circle. Right. So that's what you need it to be inscribed. You need the vertex to actually be on the circle.
On the circle. Okay. Thank you.
You're welcome. Okay. Good question. Other questions? Okay. So we're going to give one more result, which I think will be the last proof that we do today. Question.
Before you go further,
Yep.
Can you go back to the slides? Okay.
Yep.
So you just made it clear about scribe. But I'm looking at, is that inclined angle you have here? Since theta is equal to alpha plus beta, is that inclined or what you have there?
Yeah. So here's why. So look at these first two things, right? Alpha, beta, gamma makes a triangle. So they're 180 degrees when you add them all up. So, and you can rearrange and you can say that alpha plus beta is 180 minus gamma. Now, gamma and theta make a straight line. So that's also 180 degrees. So gamma plus theta is 180 degrees, and rearrange, that gives you that theta is 180 minus gamma. So alpha plus beta is 180 minus gamma. It's the supplement. And theta is also 180 minus gamma, also the supplement. So since they're both 180 minus gamma, they both have to be equal to each other because they're equal to the same thing. Okay. So another way of viewing it is that both theta and alpha plus beta are both supplements of gamma. One, you can view the supplement from a straight line, and the other one, you can view the supplement from the triangle. Okay, so that's why they're the same. So that's why theta and beta plus alpha are the same, because they're both supplements of the same angle. Okay. Good. Other questions? Okay, so let's do the last theorem for today. So what happens when you have an angle formed by a chord and a tangent? Okay, so if a chord meets the tangent line to the circle at B, then the measure of the angle formed is half the measure of arc AB. So again, it's hard to understand these theorems from words. We got to draw a picture. So let me draw a picture. So let's say that I have I'm going to draw point B over here. Sorry. Why is this happening? And I'm going to draw chord AB. And then I'm going to draw the tangent line to the circle at B. Yeah. Fine. Call that the tangent line. Okay. And so this is going to be my angle theta. Okay. And the theorem, let me just put a point here. I'll call it C. And the theorem is that the angle theta is equal to 1/2 times the measure of arc AB. Okay. Right. So this is the theorem. Okay. All right, so it's another one of these half angle. You notice that half the measure of an arc seems to show up a lot, right? It shows up in the inscribed angle. It shows up in this angle formed by two chords, and it also shows up in this angle formed by a chord and a tangent. Okay, so you can do a real proof of this, and there's a proof in the book that I sent you, but I find the proof hard to memorize and a little unintuitive, and you have to draw a whole bunch of lines. I'm fine drawing one line. I don't like drawing more than one line. So let me give you an informal way to remember what's going on in this proof. Let me give you an informal justification that's going to tell you how this proof works. Okay? So what's the justification? I'm going to draw the circle again. I'm just going to draw the same diagram. Okay. I'm going to draw my chord AB. So this is B, this is A. And now instead of drawing the tangent line, I'm going to draw a whole bunch of lines that ultimately, I'll draw the tangent line. No, let me try that again. Let me just try to draw a straight line here. No. Sorry. Sorry. One more time. I'm very bad at drawing these tangent lines. It's hard because the tablet is sort of slippery. Last time. Oh, okay, I'm feeling good about this one. Okay, that's pretty good. Okay, let's just assume this is the tangent line. Okay. Okay, so here I have my angle theta. Now what I'm going to do is I'm going to draw another line. I'll draw it in red over here. And maybe I'll call this D and I'll call this E. And let me call this angle over here, let me call this angle alpha. Right? So now what happens? Well, from previous theorem, well, this alpha is an angle made by two chords, right? So its measure is going to be the average of arc AD and arc BE, right? It's 1/2 measure of arc AD plus measure of arc BE. So if the alpha is 1/2 measure of arc AD plus measure of arc BE, right? This is the previous theorem. Okay. Because this is an angle formed by two chords. So now what are we going to do? So now let's slide line DE toward, so I'm going to slide line DE toward the tangent line at B. Okay, so what happens when we just kind of slide this line this way? So I'm going to keep line AB by itself, but I'm going to slide this line DE gradually toward this tangent line. I'm just going to slide it to the left. So remember, and this angle I think we called theta at the beginning. We called it theta, yes. So this angle we called theta. So as we slide it along, we have that as we slide it towards the tangent line at B, we get that alpha eventually becomes theta, right? We slide this longer and longer and longer. Eventually, this alpha becomes the line theta, right? Well, as we keep sliding this along, arc AD becomes arc AB, right? Because D goes to B. So arc AD becomes arc AB as we slide this along. And what happens to arc BE? Well, as we slide this along, the E gets very close to B. So arc BE just becomes 0, right? Because the E just goes to B. Right? So arc BE just becomes 0. So arc AD goes to arc AB and arc BE just goes to 0.
Yes, sir.
Yes, Prince.
A question.
Yeah.
Yeah, we have the alpha, and
Yep.
I'm seeing a theta to be a degree to where the theta is at a degree. But where the alpha is located, can there be an angle measurement to be indicated to where alpha is as well?
Well, this is alpha right here. You want me to give it a, sure, I can call this F. Okay, so alpha,
Yeah, where is
alpha, sure. If you want to call it F, that's fine. So alpha is DFA. Yeah. Alpha is DFA if you wanna give this point a name. Yeah. Okay?
Okay.
So the point is, what happens is that I could have drawn this line anywhere. So I have this alpha is 1/2 measure of AD plus measure of DE. But as I slide this thing over, if I slide my D and my E, what happens is that alpha goes to theta, AD goes to AB, and BE goes to 0. Or maybe I'll say measure of BE goes to 0. Okay? So the equation alpha equals 1/2 measure of AD plus measure of BE, this becomes what happens as I slide. If I keep moving my D and my E, this equation is still valid no matter how far I slide it over. And so in the limit, when I slide it over all the way, what does this become? Well, it becomes, well, alpha eventually becomes theta, right? Equals 1/2. Well, AD becomes AB, so measure of AB, right? And then measure of BE becomes 0 because that arc just disappears, so plus 0, which is equal to 1/2 measure of AB. Okay, and this is exactly what we want. Right, remember, we're saying that the measure of the angle formed is half the measure of arc AB. Well, we start with our chord theorem, and then as we slide it over, the chord theorem just becomes the tangent line theorem. So I would, again, not say this is not a rigorous...
Hello, sir.
Yes, Prince. Yep.
Yeah, it is a proof that because it is a proof we're proving the formula, which is theta is going to have the measure AB because it proves
Measure, sorry,
so you just
one
doing
half
a
AB,
proof
not,
to show how body
yeah,
1/2, yeah, 1/2.
1/2, yeah.
1/2 the measure AB. So what I'm saying is just the proof that we are doing that the measurement of theta is called 1/2 AB, right?
Right. And again, I wouldn't call this a proof. This is not like a rigorous Euclidean proof. I would call this an informal justification, right? But I think it's convincing. It's enough to make you understand why it's true. If you believe the chord angle measure theorem, then I'm just saying, just slide the chord over until it becomes a tangent line, and then that theorem becomes this theorem. Okay? I mean, this would not pass muster with Euclid. There is a rigorous proof that you can do, but that requires, it's a lot more complicated, and I think that it's harder to remember. 1/2, half, it's the same, it doesn't matter. So yeah, 1/2 times the measure of AB. So I find this a little bit easier to memorize, and it convinces me why this is true. Okay, to do the actual proof is quite a bit harder, and I don't want to do it. But I think having this justification why this comes from the chord theorem is useful and much easier to remember. You just draw the chord and then you just slide it over until it becomes the tangent line, and then the proof just drops out. Okay, so this is my justification for the tangent line. Want to see question? Okay, question? Any questions? Okay, I'm just going to give one little exercise, and then we have to stop we have to be done in 5 minutes. So we won't finish everything. We'll finish it up next time. But you know, as a summation, we now have all of these angle theorems that tell us how to calculate various angles in circles. Okay, and I think it's good to, and we've tried to give a justification for each of them so that at least it's something that you can look up and see. Okay, I'm going to teach about this. Let me at least make sure I remember some idea of why it's true. This is not just magic, right? I mean, this comes from arguments that you can make. So the exercise, which I'll leave, which I'm not going to do, but you can do for homework, is I'm going to draw a circle here. So in this figure, I have I have a tangent line here. I did that so much more easily. this time. So let's see. So in this figure, I've got A and B and C. And I'm going to draw this line. I've got BC here, and I've got CD. It's going to be D. I'm going to make a triangle here. So in this figure over here, we have that angle ABC is 60 degrees. So 60 degrees here. And angle BCD is 70 degrees. Okay. And this should say find, not fince, find the measure of angle CBD. So angle CBD, this is my theta over here. So exercise, calculate theta. Okay. And okay. Oh, and maybe a second exercise. Yeah, so I'll do these two exercises. We can go over them tomorrow. So second exercise, I have a quadrilateral ABCD. Sorry. So I have a quadrilateral ABCD inscribed in a circle is below. And so angle DAB, maybe I'll call that alpha. And angle BCD, I'll call it beta. And the question is, so calculate alpha plus beta. Okay? And I'm not going to tell you anything more, but I claim that you can give an actual answer here. So calculate alpha plus beta. Okay? So let's go skip this all, and there's a little bit about ratios, of course. Yes, hello?
Yeah, the diagram you just drew.
Yeah, maybe don't give it away if you know the answer. If you're going to give the answer, let's let the other folks think about it who may not know it yet.
Okay, because I want to get a hint on it.
You probably know let's let people think about it for the week, and next week we'll discuss it, and you can go over the answer.
Okay,
great.
Easy, very easy.
Yeah, no, that's the hint is that it's easy, but you have to think a little bit. Okay, so we'll skip these slides. We'll do them next time. I do have to finish up. So there's a lot of theorems in one day. Next week, it says we'll begin a mini workshop on differentiation and integration. We'll probably still spend we're going to spend the first half of next week on circle theorems. Okay, so we're going to do differentiation integration. Now, you can spend a very, very long time on differentiation and integration, and we're going to have to be restrictive on what we cover. So you are more familiar with the high school curriculum than I am. So it has differentiation and integration as an element of the high school curriculum. Certainly, I can't believe it would cover all of the material in a standard calculus textbook on differentiation and integration. So if anybody's experienced with this and wants to write with the chat room, it would be good to have a sense of how much differentiation and integration is it really expected, let's say in an ideal situation, that would be covered in this grade 12 curriculum, because it's there in the grade 12, but I don't know exactly how much is expected to be covered. And I'm sure it's different at every school, and some schools you may not get to it at all, and sometimes you do. But if everything worked correctly, I want to know kind of what is the ambition of what to cover in high school on differentiation and integration. So and I'll pose this question in the chat room so that somebody could say, if everything worked perfectly and you were ambitious, how much realistically would one want to cover in high school? And I think we'll focus on that part of the differentiation and integration. So I'll send out this question again on the chat. Okay? But we'll meet next week. We'll finish up circles and we'll move on to planning basically the differentiation and integration workshop. And I'll send out the notes as always. Please write your name in if you haven't done so already. And thank you for your attention.
Yeah, Dad, before you leave.
Dad, thank you so much.
You're welcome.
Yeah, before you leave.
Yes, Emmanuel.
Hello?
Yes, Emmanuel. Hello?